Thank you. Thank you first for the invitation. It's always a pleasure to come to Cargèse. And today, so I will give this lecture. So this is a lecture. That is to say, 90% of that lecture is about an overview of different machine learning techniques that can be used for quantitative imaging. Only at the very end, I will give you a few original results. But the objective of the talk is really to show what are nowadays the ideas that people coming from machine learning try to apply to imaging. So what I call imaging is not image processing. It's really imaging according to the way you do it. So I will call it sensor array imaging. That is to say, we want to image an unknown medium. So depending on the application, that can be the human body in medical imaging, that can be the Earth's crust in seismic imaging, and so on and so on. There are many modalities using many different types of waves in many different configurations and geometries. But we may say there are always two main steps, an experimental step, the data acquisition step. That is to say, you want to image an unknown medium. You deploy an array of sources that will transmit waves that will propagate through the medium. You deploy an array of receivers that will collect the waves that are either reflected or transmitted by the medium. That will give you a lot of data. And then comes the data processing step. You take this data set and you want to process it to reconstruct what is inside the medium. So, as I said, you have many modalities. Here is one modality that works, I would say, pretty well, ultrasound echography in medical imaging. On the left, you have the data acquisition step with the array of transducers here that can be used, as you know, both as sources and receivers. And on the right, the reconstruction of the target. Here, a nice baby. So from a mathematical point of view, because as you may know, I am a mathematician, for me this is an ill-posed inverse problem. So I will describe what I call an inverse problem, and in particular an ill-posed inverse problem, and why machine learning can be useful to solve them. So here is another example in which we can visualize a little bit better what is a forward problem and an inverse problem. So now it's another modality, it's reflection seismology, seismic imaging. So on the top, you have, in some sense, the forward problem. So you can see the medium here. Let's say here what you can see is the index of refraction or the velocity map of the medium. For those who know, this is just a Marmouzy model. And here you have the picture that models the acquisition geometry. So the red spot is a point source, a point-like source, an air gun. And the triangles are hydrophones, that is to say receivers. And what you see here is what I will call a snapshot. That is to say, this is a spatial profile of the wave, the pressure, at some time. So the forward problem is given the medium to be able to compute the waves that propagate through that medium. So the forward problem is easy to solve. You need a wave solver. And so it's easy to compute this kind of snapshots and to compute the signals recorded by the 8 receivers here. So you can compute easily, given the medium, the time traces recorded by each receiver. So this is the forward problem. Given the medium, compute the signals recorded by the receivers. But what we want to solve, of course, is the inverse problem. That is to say, given the time traces, we want to reconstruct the medium. So mathematically, I rephrase everything in mathematical terms, but I will use a very simple model. The forward model is, as I said, you know the velocity map, the velocity model, the three-dimensional velocity map inside the medium. And the forward problem is compute the wave field. So here I will use a scalar wave model. So let's say acoustics, if you want. A scalar wave model where the wave field is solution of the scalar wave equation with that particular velocity model. And on the right-hand side, you have the source term, so a point source at xs, that transmits something, a pulse psi of t. So the forward problem is to compute the signals recorded by the receivers. So here, to simplify, I will assume that I have n sources and n receivers that are collocated so that I have a single n. But it may be more general than that. And so at the end of the day, what you record is a matrix of signals, so DRS of t, so t is the time, and that means this is a signal recorded by the receiver at XR when XS is used as a source. So this is the forward problem, given C, compute this response matrix. But as I said, what I want to do is to solve the inverse problem, that is to say, given that guy, reconstruct the velocity map. Okay, how do we do that? Well, the gold standard method, in fact, it's called, it has different names. Let's say in seismology, it's called fuel waveform inversion. And it's a very simple idea, but it's a very powerful idea. The idea is just you will do least square minimization. That is to say, you will, so you have your data set, the measured data, and you have a wave solver that is capable, given any velocity map, to compute the traces that would correspond to this velocity map. And you will solve a big minimization problem in which you try to minimize. So it's a minimization problem. You minimize over all possible velocity maps the misfit between what you have observed and what you would observe if C was the velocity map. So you try to tune the velocity map so that the predicted signals correspond to the observed signal. So of course this makes sense, because if there is no noise whatsoever anywhere, if your wave solver is perfect, then indeed, if you pick the right C, then that should cancel and you will reach the global minimum of this functional. So that's the gold standard. So it's a big minimization problem. It has been studied for 50 years. So here is a nice review about this problem. So from a mathematical point of view, we call that a PD constraint minimization problem. So everything is there. Minimization, yes, we have to solve a minimization problem. A complex one, because search space is a functional space. You have to look after all possible three-dimensional velocity maps. So it's a complicated optimization problem, but it's PD constraint in the sense that this guy has to solve a PD, the scalar wave equation. So what you do typically, and this is what is discussed here, is you will use your favorite optimization algorithm, and the most powerful one are iterative optimization algorithms. So here I list a few of them to try to determine, to solve the solution of this minimization problem. So of course, as you may know, people have been working on that for 50 years, academic, industry, and so far it's not so well controlled, so well understood. There are still a lot of problems. Of course, the first problem that you can easily imagine is that it's really computationally expensive, because all these methods are iterative. That means they require to call many, many times the wave solver. So you have to call many times the three-dimensional wave solver. It's not completely free. And more important, this objective function looks nice. It's a quadratic misfit. It's least square minimization. But the problem is that the forward map is not linear at all with respect to the velocity moment. The PD is linear, but as a function of C, it's highly nonlinear. So this guy is highly nonlinear, so that this misfit function, in fact, is not at all quadratic. It's not even convex. In fact, whatever the property you may think at, a good property, this functional will not have it. So it has, it's not convex, highly nonlinear, it has many local minima, it's a nightmare. So that means that, we have a problem. If this guy is really complicated, has a lot of local minima, that means that when I run an iterative minimization algorithm, the algorithm will go directly to the nearest minimum close to the starting point of your iterative algorithm. And if you have many, many local minima, you will never get the true global minimum. And just to illustrate that, this is an example, a very, very simple academic example, but that will illustrate what I mean, that it's a complicated problem. Here is the class of velocity model I will address just for this academic example. So it's very simple. My medium is just a superposition of two homogeneous half spaces. That's all. And on the top of it,
in your way of solving the problem,
yes.
Do you take into account physical requirements?
Yes, of course.
For example, the C, in your case, it looks to me that it can take continuous values, while in the real life...
Yeah. We will see that. That's part of the regularization that will come just after. Yes. We will take all possible physical constraints that we will put in the prior, and then we will see that there is a way to learn the prior from the data themselves to be more and more efficient. That's the whole point of that talk.
But this, it will create later on problems, because if you try to use gradient optimization,
yes.
Then you will not be, so to say, physically allowed to go to C plus delta C, because maybe this C plus delta C is not allowed. So
yes, that's why we will do something else than gradient or this particular optimization algorithm that I have proposed. We will see other algorithms to solve the minimization problem. But here, just to see that this guy is in fact, this objective function is in fact very complex. As I said, my class of visuality model is very, very simple, just two homogeneous half spaces. I will assume, to simplify even more, that I do know the velocity in the upper half space, and all the crosses that you can see here, these are sources and receivers. So each cross can be used as a source, and all the receivers record. I assume that I have a dense array here, sampled at, let's say, smaller than half the wavelength. I sample in time even below the Nyquist frequency, so it's as if I was continuously recording in time. So what are the unknowns? So a priori I have three unknowns: the depth of the interface, the angle of the interface, and the velocity in the bottom interface. Three unknown parameters. In fact, I want to plot a 2D plot, so I will assume that I know which one of the three. I will assume that I know the angle. So I know the true angle, I know the true velocity on the top, so I only have two unknown parameters: the velocity in the bottom and the depth of the interface. So I have 20 gigaoctets of data, I have two unknown parameters. The model is perfect, there is no noise. Come on, guy, I should be able to do it. And here is the plot of this objective function. And you can see that indeed the global minimum is indeed right at the true values with which I will generate the data. So, okay, the global minimum is just here, but you can see that this guy, as a function of the two unknown parameters, has many, many local minima. So this is a typical landscape that you deal with when you do full waveform inversion. And this is a very simple example. The model is perfect. The data have been generated with the model. There is no noise. And I have only two unknown parameters. In reality, of course, I will have to determine a three-dimensional velocity map. So that is to say the search space is of dimension at least 1 million or 1 billion. So you may imagine that you have such a function in dimension 1 billion to minimize. The number of local minima is tremendous. So how do I solve this optimization problem? So people are considering this question for a long time. So let's say okay, I would say from the 80s to a few years ago, these were I would say the state of the art. To try to solve this minimization problem, the main idea was to try to regularize it, that is to say to put some additional constraints, either physical, either a priori, judgment expert, and so on, to try to make this objective function maybe not fully convex, but let's say more convex, so that when you start from a reasonable starting point, an iterative optimization algorithm, it will converge to the true minimum. So here you have a list of the first regularization that were tried. So in particular, TV total variation is popular because TV means that you expect that the velocity map will be stepwise constant. TV means you penalize the L1 norm of the gradient. So L1 means you try to put as many things to 0 as possible. So L1 norm of the gradient means you try to put the gradient as close to 0 as possible. So that means you want something stepwise constant. So TV works quite well. I mean, I would say this is one of the most popular and used regularization. But nevertheless, it's not enough. So you have to do additional things. So here I give a few recipes. So the first two are a little bit ad hoc. They have the same spirit, the first two. One in the, let's say, in the time of spatial domain, and the other one is the frequency domain. So layer stripping is, in fact, you will not try to solve immediately the fuel problem. You will just try to reconstruct the medium close to the sources and receivers first, using the early data, the data for small times. So you just solve close to the sources and receivers using the early data. Maybe the hope is that it's a little bit well conditioned, this inversion problem. And once you have reconstructed this guy, you can try to reconstruct what is slightly below using later data and so on and so on. So that gives some good results from time to time, but not always. You have the same thing in frequency. That is to say, you do not try to invert immediately the whole problem. You will first try to get, let's say, a low frequency, a low spatial frequency approximation of the velocity map using the low frequency data. Maybe it's a more well-conditioned problem, and then you incorporate more and more high-frequency data as the optimization goes on, and you hope to reconstruct higher and higher spatial frequencies of your domain. So these are, I mean, two recipes that people are still working on. Also, they are 30 years old. People still try to improve these methods. Then a little bit more recent is new ideas. This one already is a kind of a flavor from machine learning. The idea is that, okay, here we try to minimize the quadratic misfit. It's a quadratic norm over the data. Maybe we should use another norm. And people have tried, well, that was not the first test, the first time that people try to use another norm. But here is a norm that comes from machine learning, from optimal transport. We will see that again. And they have replaced this quadratic norm by this optimal transport norm that is more capable to, let's say, compensate for, in particular, cycle skipping. So we will see that later. And then you have a huge series of work still going on about extension or relaxation strategies. It's about the fact that here it's PDE constraint. This guy is really the solution of the PDE. Maybe we can relax that a little bit. We do not ask immediately that it solves exactly the wave equation. We will enforce that progressively. That's the main idea of this last series. Okay, but anyway, at the end of the day, it doesn't work so well. So we will take a step back just to understand what's going on. So here I rewrite a general inverse problem with the same point of view as the one I have adopted just before, that is to say least square minimization. So the inverse problem is now x will be the input, y will be the observation. So I assume I observe y, and I want to reconstruct the x, the input that corresponds to this observation, through a forward model f. So I try to minimize again the data misfit between the prediction f of x and the observation y, with some penalization, as I have seen. This is important to use this kind of penalization when you deal with very ill-posed problems. So in FWI, the x was the velocity model, the y was all the response matrix, and the f was this forward wave solver that gives the time traces at the receivers given the velocity model. But here is a general inverse problem regularized or penalized by some penalization terms R of x. So one of the main questions I will address is how do you choose R of x? And we will see at the end of the day, we don't have even to choose it. We will build it. Just to relate that to another point of view on inverse problem, the Bayesian point of view. In the previous slide, the idea is we look after the best estimate, the best guess of the best X that fits as best as possible the data. Bayesian point of view is a little bit different. We don't look after the best estimate, a unique X a priori. What we want to build is a kind of probability or likelihood measure that gives to any possible X the probability that it has generated the data that was observed. So the probability of X must be small if X is really not compatible with the data, and it must be high if it could have generated the data. So how do I get this probability measure? In fact, the answer is trivial. It's given by Bayes' theorem that tells you that the probability of X given Y is up to a multiplicative constant proportional to the probability of Y given X times the probability of X. That's Bayes' formula. Well-known formula. And then you can see that, in fact, you have these two pieces. The first one is typically well-known because the forward problem is well-characterized, well-known, and this depends on the forward problem. What is Y when you know X? So this is what we call the likelihood. And P of X, that's a prior model, what you know a priori before even collecting the data, what you know about X. So for the full waveform inversion, maybe you know indeed that, okay, X has to be positive, have to have some smoothness or not, maybe stepwise constant. Okay, you put a lot of a priori information in this prior information. And for instance, a typical likelihood model is the one that corresponds to a Gaussian white noise model. That is to say, the observation Y, if you know X, is just f of X plus Gaussian white noise. And in that case, the likelihood of Y given X is the probability density function of a Gaussian with mean f of X and with variance, the variance of the Gaussian white noise. So that's the likelihood. Yes?
Maybe I missed it, but is the f of X known in this case?
Yes, f of X here is known. We know the forward problem. The issue is to solve the inverse problem. Here, f is known. Okay, so what is the connection between the two approaches? In fact, they are equivalent. Because if, I take my Bayesian viewpoint, so I have my posterior distribution, which is now this term, and if I want to simplify the Bayesian approach, instead of manipulating this whole posterior distribution, I want to summarize the information carried by this posterior distribution by just one estimate, which is the mode of this posterior distribution, the X that maximizes the posterior distribution given the observation Y. So this is called the maximum a posteriori. That is to say, you want to maximize the posterior distribution. So to maximize this guy is equivalent to minimize minus log of the same guy, of course. Minus log is decreasing. But this log of P of X given Y, you may say it's a log of all this term. So when you take the log of this term, the log of exp, but that's easy, it's just this guy. So multiplied by 2 sigma squared, I just have that, the negative log likelihood. And I have a log, so I have a log of this term plus the log of this term, so I have the log prior. So you end up with the maximum a posteriori is a solution of a minimization problem in which you minimize the quadratic misfit with some penalization term. So in fact, you have exactly the same formula as the one I had in my first slides. That is to say, these two approaches are in fact equivalent, and you can make an analogy between the penalization that we had imposed in the quadratic misfit approach with the log prior that we impose when you do a Bayesian analysis. These two guys have to be related, and so that will open some ideas about how to choose this guy from this interpretation. So here is, one slide, all the ideas that you can have to try to solve this problem coming from, okay, I would say artificial intelligence. So the first two, I will not spend a lot of time on it. They are very general. They are not at all specific to sensor array imaging. You can use it for many, many other tasks. It's operator learning, that is to say how to train a neural network to mimic some operator. So in fact, it's how to build an efficient surrogate model. We will see that. And physics-constrained learning, which is we will relax, it's in the line of this idea that we will relax the constraints, the PDE constraints, by saying, okay, we will not enforce exactly that the solution has, the wave field has to solve exactly the wave equation, but we will enforce it in the loss. So this is not specific to wave-based imaging, but it can be used for wave-based imaging, we will see it. And these three, I will spend a little bit of time on these three approaches. These ones are really dedicated to sensor array imaging, or let's say imaging problems. It's how to learn the prior, and I will spend some time about the so-called plug-and-play method. We will see that, in fact, you can use some interesting objects that will play the role of priors. Then we will push even further and show that, in fact, we don't need to have an expression of the prior. What we need is to know how to sample a prior. And then we will be able to use modern generative methods, modern generative models that will play the role of priors in this sensor array imaging. And at the very end, I will end up by that with some very recent results. In fact, here we learn the prior. Here we will learn the whole loss function. I will show you how you can learn the whole loss function and end up with a new loss function that will be perfect. That is to say, it's convex and plum. You just have to run a standard optimization algorithm and you will find the global minimum. So that's the very end. So here, operator learning. So it's a huge industry. The idea is just that, okay, in sensor array imaging, you need to call many, many times a wave solver. That's expensive. So maybe we can learn a surrogate model of the wave solver. So that's the idea. Use this huge machinery, this different neural network architecture that will be able to mimic a wave solver and be run very, very fast. You can call it many, many times, and hopefully you will be able to solve the inverse problem more efficiently. So that's the whole point. Build a fast surrogate of PDE solvers. So it works, I would say, very efficiently in some domains. You may know, I don't know, for instance, in weather forecast. Navier-Stokes equation, which is a quite difficult PDE, can be solved by these methods very, very efficiently. They become, they beat everything compared to highly accurate schemes to solve Navier-Stokes equation for the coupling of atmosphere and ocean. But for sensor array imaging, so far it doesn't work so well. There are still a lot of problems. But this comes from the fact that, okay, you may build a reasonable wave solver, but when you plug it into the inverse problem machinery, in fact, you realize that it's not good at all. It will be pushed towards domain where the extrapolation is not good, and you will fail miserably. So far, this approach for solving sensor array imaging problems has not proved to be very efficient, but it has proved to be very efficient in other fields. Another one is physics-constrained learning. This is the idea that maybe we will relax the PDE constraints. And so the idea is the following one. Instead of claiming that U is a solution of a scalar wave equation parameterized by the velocity map C of x, you will say that these guys are in fact the outputs of a big neural network with input tx and with a lot of parameters theta. So theta is, are the parameters of big neural networks. So theta with a dimension between 1 billion and 1,000 billions. So you have a lot of free parameters that you can tune so that, hopefully, you can find the right pair U and C. And to train this neural network, you have to build some architecture, and you have to propose a loss function, the function that you have to minimize with respect to theta so that you are happy with the choice of the parameters theta. And here you will have to impose a few things. First, that this U theta fits as best as possible the measured data and the source, and also that is solves as best as possible the scalar wave equation. So you do not enforce that this is equal to 0, but you put the norm of the residual of this PDE into the loss function. So when you minimize the sum of these three terms with respect to theta, if you find something that is very close to 0, that means you have solved the inverse problem. The C theta that you have obtained is exactly what you are looking after. Okay, again, this strategy works well. For instance, in this paper, you can see a list of problems that can be solved using these ideas. But unfortunately, nobody has been able to make it work for sensor array imaging.
The idea is that you train a network.
Yes.
You will minimize this of a lot of training examples.
Ah, yes, of course, you need a lot of...
In test time, you have one set of measurements, and you try to find the best data that will explain this.
This one, yes, exactly. So it's really computationally intensive. You need data, and you need really an offline, I would say, training, which is quite expensive. And even if you have a lot of computational power, so far, it's not so good. Okay, I've never seen a paper showing that it was working. I tried myself. I couldn't make it work. I mean, yes, you can make it work by, in some sense, cheating a little bit, helping tuning of the parameters, but it's even more, in some sense, it's even more difficult to tune the parameters than to solve the inverse problem, so come on. It's not, so far, it's not a good idea. Okay. Now, okay, I will try to show you a few techniques that have shown that they can work. So plug and play prior. So the idea is to learn a prior. So I need a little bit of background. So here what we have to solve is a minimization problem in which we have a sum of two terms, a quadratic misfit, say, plus a log prior, negative log prior. Okay. Okay, when you have the sum of two terms, you realize that these two terms are a little bit different. You add very different objects here. So you minimize with respect to the same x, of course, but these two guys have different flavors. And so people start to think, oh, maybe it's good to try to solve that by splitting. That is to say, you try to minimize a little bit with respect to the first one, then with respect to the second one, then with respect to the first one, and alternatively. Maybe it's a good way to do it. Okay. So that's the first idea. Second idea is about how do you solve this optimization problem. So first, if you have a standard minimization problem, the basic, I would say, optimization algorithm is gradient descent. You want to build a sequence xk that will converge to the global minimum x star. And for doing that, you start from starting point, arbitrary. And then you want to build an x1, then an x2, then an x3, for which f of xk is decaying. Ultimately, decaying so far so good that you will get the minimum. And how do you do that? Imagine you are at xk, so you compute f of xk if you want, but you would like to move a little bit to reduce, to go below the value of xk. So to do that, you compute the gradient of f at the point where you are. So of course, if you follow the gradient, you will increase f. So what you do is you go the opposite direction. So you start from xk, and hop, you go a little bit in the opposite direction of grad of f of xk with a small step tau. And you do that again and again and again, and that's the idea under nice, let's say, properties of f. I will not discuss that too much. You will converge to a local minimum. Okay. So that's the basic optimization algorithm. That's another one that people started to work, well, I would say 20 years ago. Proximal algorithm, and you will see, in fact, it's very, very close to this one. So what is the proximal algorithm? It's again, okay, an iterative algorithm. So you compute xk plus 1 from xk. And to go from xk to xk plus 1, you have to solve an optimization problem. But this one is, thanks to this term, typically strongly convex. So it's very easy to design an algorithm that will solve this guy. So that's doable. So what's the difference between this and this? In fact, not so much. If f is smooth, that is to say f has a gradient, then the solution, I mean the proximal, the z hat, that is the proximal of some x here. So it minimizes this function. So if it minimizes this function, it's at z hat, the gradient of this function must be 0. So this is what I write here. And when you write the gradient of this guy, so the gradient of a quadratic form, it's a linear form. And here you have the gradient of f. So when you look at the equation satisfied by z hat, and you plug that here, so x here it's xk, z hat here will be xk plus 1. So you have xk plus 1 plus tau grad of f of xk plus 1 equal xk. So when you compare this with this, it's almost the same thing. Almost, because here this is what we call in mathematics an explicit scheme. Xk plus 1 is xk plus a correction that depends on xk. And here it's xk plus k equal xk plus a correction that anticipates the move. But it's exactly the same move. Huh? It's minus tau grad f. So these two guys are pretty close to each other, except that this one is implicit, that is to say, more stable. I will summarize the mathematical advantage of using explicit schemes is that it is more stable. And not only is more stable, but it does not, in fact, this calculation is done for a smooth f, but you can apply the proximal algorithm even when f is not differentiable. Yes?
Do you have an intuition why you use that, that second function to minimize?
Because of that. Because essentially it's more stable and it can be used with function f that has that are not differentiable. You don't need to compute the gradient of f when you solve that. Here, this is what we call a first-order optimization algorithm. You really need to compute first-order derivatives. To compute that, you don't need it. So you really can apply it to a very arbitrary function f. And in fact, this is what happens in our problems. So in our problem, we have to minimize a sum of two terms. So the first one is, as I said, typically the quadratic misfit. So if your forward model is smooth, this guy is smooth. Oh, there are two f. Oh, shit. So this f is the forward model, and this one is the one that is here. Sorry, that's a big typo. There are two f. So this f here is the quadratic misfit. Okay, so as I said, if the forward model is smooth, this f is smooth, so you can use gradient descent for this guy, no problem. But for this one, often, we have a negative log prior. We don't control exactly what type of prior we use. In particular, if you use something that looks very reasonable, a TV norm, this guy is not differentiable. Ah, bad luck. If it's not differentiable, I cannot use gradient descent. So then that makes sense to use proximal. But you could use proximal of the sum of the two, but you can use gradient descent for f and proximal for the second one. In fact, if both f and g are differentiable, you could use gradient gradient, proximal proximal, proximal gradient, gradient proximal. I mean, you can imagine all kinds of combinations. So some of them are better than other ones. So these ones are the advantage that it has convergence guarantees and that it can be run even when G is not differentiable. So that's a very nice algorithm to solve this optimization problem when you have a sum of two terms. It has a different name. The first name was proximal gradient descent, and now it has different, there are improved versions that are called ISTA or FISTA, fast, ISTA, and so on. But I will not describe the tuning of this idea. But now, let's move a little bit even further. How can I imagine what the proximal of a negative log prior is? But in fact, it's a denoiser. This is what I want to show here. Consider a very simple denoising problem. You have an unknown z. You observe x, that is z plus noise. So you imagine your z is corrupted with some, here, Gaussian noise. And you want to extract what is the best from the observation x, what is the best estimate of z. So we assume that we have a prior, P on z. We know that z is a realization of a distribution with PDF P. So what is the best estimate of z given x? Again, that's the argmax of the posterior distribution of z given x. The posterior distribution of z given x, I can write it by Bayes. It's the likelihood, the distribution of x given z, times the prior. This guy is here. I can put minus log here, and I have an argmin. And when I have a minus log of the product, I have the minus log of the first term, minus log of the second term. The minus log of the first term, again, given z, x is a Gaussian with mean z and variance sigma squared. So the minus log likelihood is just 1 over 2 sigma squared z minus x squared. Okay, you look at that, and you compare with what I had written about what is a proximal algorithm, TAC, which is here. It's exactly the same thing. So in fact, my proximal algorithm is a denoiser. The proximal of a negative log prior is in fact the solution of a denoising problem using that prior. Okay, so that's an interpretation of proximal. So what's the point to make this observation? Well, that's the point of the introduction of a plug-and-play algorithm. If you have such a minimization problem to solve, so let's say a data misfit part plus something that is a regularization term, that can be interpreted as a negative log prior, that can be interpreted as a denoiser, you can do proximal gradient descent. So a step of gradient descent with respect to the quadratic misfit, a step of proximal with respect to the negative log prior. We have observed that, in fact, this is a denoising problem. If the denoising problem is just Gaussian additive noise, it's exactly the same thing. There is no difference. So you can write this as an optimization algorithm with a Gaussian denoising method here. But in fact, why not to use any other denoiser? So that was the idea raised 10 years ago. Of course, people in signal imaging, processing, signal processing, and so on, they have been working for 80 years about building denoising algorithms. So just pick the denoising algorithm that you have on the shelf and apply it here. That will play the role of this guy. And suddenly, all you have to try is all the denoisers that you have on the shelf in this algorithm, and either mathematically or empirically observe what happens and show that you will converge to the global minimum. So that's the idea of plug and play. This is really that. You plug in this formula a denoiser, your favorite denoiser, and you run this algorithm. That's plug and play. That's all. So what type of denoiser should you use? Of course, you have a lot of denoisers. I list I mean, the list is infinite almost. Huh? The ones that existed before 2013, before this introduction of this ID, and then the, let's say, more modern denoisers that have been built specifically for the task I have described just before. Of course, they are built on neural network architectures, and they give very, very, very reasonable solutions. So it's really something that is very competitive. If you look at machine learning conferences, you always have mini symposia on imaging problems. I think you will see half of the talks are around plug-and-play methods. So, because of course you can imagine you can write many different versions. So everybody is trying its own version, claiming that it's better than the one of the neighbor. Of course, when you select the examples, it's quite easy. But it's a good idea. Indeed, it opens a lot of possibilities, and it has given rise to, okay, as I said, many nice ideas. Oops. Okay, so now plug-and-play methods, in fact, as you have seen, they replace the proximals of a log prior by a denoiser. So in fact, you could, by working hard, reconstruct from a given denoiser to which prior it corresponds, but you don't need it. You don't need to express explicitly the prior that you are using. You just use the denoiser. And people push this idea even further by saying, maybe I don't even need a denoiser. What I will need is something that will play the role of a prior without specifying what is the prior, but by using modern generative models that will be able to sample without an explicit expression of the prior. So I want to show you what I mean by that. So generative models, so it's an introduction to generative models, and I will introduce the one that is nice to introduce here because it's based on time reversal. So what is the purpose of a generative model? It's to build a random generator that will be able to generate realization of a distribution with some given probability density function, say. But the idea is we already have a lot of generators, but we want to build generators that work when the object that we want to generate has high dimension. So typically an image. An image, it's a collection, I mean, you may say it's a point in RD, where D is the number of pixels. That's for a black and white image. If you have color, you have to specify RG, I mean red, green, blue, so that will be R3D, but it doesn't matter. So the idea is we want to generate images from a given PDF. So in fact, it's not even that. We do not know P0. All we know is a sample of given images. So you can imagine human faces. You have a collection like that of human faces. And you want to build a generator, a random generator. When you call it, paf, it will generate a new human face. Not one pick randomly inside this set, that's stupid. Something that looks like a human face, that has all the characteristics of what we represent ourselves as a human face, but not taken from this space. But we will use this set as a training to build this generator. So you know that it exists. If you go on this website, for instance, you click enter, 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 and it generates faces, 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 faces that do not exist. They are completely, this is a random generator here. This image is random. You will never find it again if you go back to the website. Every time you go back, you will get something new. So that's the target. Generate this, build this kind of random generators. So we will do that based on diffusion processes. So what is a diffusion process? Okay, essentially it's a like an ordinary differential equation in which you add noise. So if you forget this guy, this is just an ordinary differential equation. And imagine you solve an ordinary differential equation, and at each time step, not only you add this drift, but you also add a small Gaussian noise. So that's what I call a diffusion process, and this is what I call a stochastic differential equation. So one that is very simple is the Brownian motion, is the one in which you have zero here, it's just noise. So it's a diffusion process. When you look at what it looks like, it's something very Ross, continuous, Gaussian. It's not the one that we want because we would like something that has some nice ergodic properties. So a typical example is what we call the Einstein-Uhlenbeck process. So you see it's a solution of this stochastic differential equation. So at each time step, in some sense, you reduce a little bit the x and you add noise. And you do that repeatedly. And you can imagine that when time increases, but eventually you forget the initial state and it remains only noise. You remove the x as time goes on and you add more and more noise. So at the end of the day, you just have noise. And I have calibrated it carefully. I have put -1/2 here so that at the end, I have a normalized Gaussian white noise at the end of the day. That is to say, the coordinates of xt are just independent Gaussian random variables with mean 0 and variance 1. When t goes to infinity, this is what happens. So this is a general diffusion process. This is an example of an ergodic diffusion process. Okay, so let's consider such an ergodic diffusion process. Maybe the Einstein-Uhlenbeck, but maybe another one. So you have a drift term, a small Gaussian noise, additive Gaussian noise. Assume that you start from an x0 taken from this target probability density function P0. So what do we know? We do know that we have an ergodic diffusion process. So we know that as t goes to infinity, xt forgets about its initial condition. It converges to the stationary distribution of the SDE. So if you have an Einstein-Uhlenbeck process, this is what I said, whatever you start with, after a long time, you forget about the initial condition, you have pure noise. Okay? So that's what happened in the diffusion process. So that's very different with waves. With waves, you can propagate even in a very complex medium. At the end, you still have the memory of the initial state. Here, you forget completely the initial state. But we would like to do time reversal. And that was done before time reversal for waves. That was done in the 80s. In the 80s, people worked on time reversal for diffusion processes. Is it possible to go back in time? And the answer, surprisingly, is yes. So how does it work? You build a new diffusion process. So you will start from some large time, capital T, from the distribution P capital T, and then you run a diffusion equation backward in time. So again, adding noise, removing blah, 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 this drift, but you need this correction. So if you have no noise, of course, to run backward an ordinary differential equation is very easy. You run the same equation backward in time. So g squared is 0. So you run backward an ordinary differential equation without any problem. When you have this noise term here, you need to incorporate this additional drift when you go back in time so that you can get the result that at any time t, this guy has exactly the distribution of the forward process. So in particular, you start from time capital T, you run backward in time this diffusion process. At time 0, you will recover exactly P0. And so what is this special drift here? It's a complex object. We call that a score. It's a grad of the log of Pt of x. But it does exist. We do know that if you select the right drift here, you will be able to go back in time. And it works even if you take t very, very large. That is to say, you start from pure noise. P infinity, as I said, it has completely forgotten about P0. It's a pure noise. You start from pure noise. You run backward in time this diffusion process, and you do know that at time 0, you will recover P0. So that's a way to build something that is very nice. So here is an illustration of what happens in small dimension, in dimension 1. Let's assume that P0 is just a bimodal distribution. You have two peaks. And you run forward, so you sample from this distribution. So you sample 6 points. Okay, 3 are taken here, 3 are taken there. Then you can see the trajectories of the forward diffusion. Here it's just very simple, it's Ornstein-Uhlenbeck. So after a long time, you forget completely about the initial condition. You just get a distribution that is a big Gaussian. And now you run backward this SD with this score here. And at the end of the day, you will recover exactly the distribution P0. So that means you start here from pure noise. Poof, you will get a sample of this distribution. So if you sample randomly here, you have a random sample here. And this ID works whatever the dimension. Yes?
It doesn't violate any thermodynamics?
No. No, because the information is here. You have a drift here that depends on the target. But it's the deterministic drift. That is to say, when you pick randomly a point here, you will take a new realization of this target here. So the idea is to build a random number, a random generator, that every time you sample a new element of this guy, which is easy, it's just pure noise, you run backward this guy, and you will get a new sample of this target distribution. So that works. Yes.
Which is just adding noise and familiar.
Exactly.
In your case, this F includes some physical operator. It's like
yes, in my case, F will have some additional stuff, but but you can do that. This is done with just Ornstein-Uhlenbeck. This one for or here. This is the first test. You imagine. That's the forward. So you start with a nice dog picture. So now D is 1 million. That's 1x. You add noise, blah, blah, blah. You remove progressively the image and you add noise, blah, 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 blah. So at the end, you have pure noise. You do that many, many times. That will allow you to learn PT of x. So that will allow you to learn the score. And then you start from a new pure noise, completely independent of everything else, just independent Gaussians here. A white noise picture. You run backward this guy, and you will get, boom, the image of a new dog. And the one that I've shown you with the faces, it's that one. It's exactly that.
Do you know G of t?
Sorry?
Do you know G of t?
Yes? Yes, it's that. G of t, that's, you could take G of t equal 1, it will work, but the idea is to make this whole process as fast as possible. And then, that comes from the detailed calculation, but you do know that the optimal G are not constant. You should go slowly at the beginning and faster at the end. So it's a fine-tuning to improve the efficiency, the speed of the algorithm, but it does not change the qualitative picture. It's just to increase the speed of the method.
So how many do you need data to learn forward?
Not so much. That's the idea. A few thousands are enough. Even so, typically D is 1 million. So but the question is, how do you learn that guy? Because x, as I said, is in dimension 1 million. Wow. So I need to learn a function from r to the power 1 million to r. Oops, yes.
How do you know that you lost the memory of the initial position?
Because I have to select here an ergodic process here. So here I need to select the F so that I do know that this guy is an ergodic process with an invariant distribution, that is what I call here noise, that has the correct properties. So F and G are chosen so that this process is ergodic.
But you have to wait long enough, right?
I have to
Wait long enough.
This is what I said. If you take G equal 1, you have to wait a long time. The idea is don't take G equal 1. You have to play with G of t so that it is very efficient and the, let's say, the stationary distribution will be reached very quickly. So the question is how to learn that? And we want to learn it from just a sample of x1, xn. And the first time I saw this idea, that was not mine, I thought this is not possible. They will never make it. And in fact, it has worked immediately. So it started in 5 years ago. The guy was really optimistic to think that he could make it. But when I read the paper, I immediately tried, and it worked immediately. I was really surprised. You shouldn't hesitate. X, as I said, it's a very high-dimensional object. You will try to learn a neural network, a very big neural network with more than 1 billion parameters. And you will try to tune this guy to match this by solving, by designing an appropriate loss function that will allow you to learn this neural network. And surprisingly, the number of images that you need is not so large. A few thousands is enough. And now we even have a new method. That was the first generations. Now we really have some method that works even with smaller images. Okay, you have two types. The ones that you have to train from scraps, and the ones that you can, let's say, train with just a few images, between 5 and 10, but you use a pre-trained neural network that was trained to generate, let's say, similar images. So for instance, you take human faces of adults, so it generates human faces of adults. You give it 5 images of baby, and you retrain, and you have a perfect generator that will generate random images of baby. So it's really impressive. So this is really something that is nice. And of course, okay, this is funny to do nice applications in image processing. For instance, imaging. This was the original image. You remove this, and you want to reconstruct the image. If you use a standard algorithm, I'm not sure what you will get here. But now the idea is that we will use these generators as priors to solve an inverse problem in which we want to reconstruct the best estimate of this image given that we have only that. And that's possible. So there is one bad way to do it, is to redo everything. That is to say, we want to generate X from the conditional distribution P0 given the observation. So you can repeat everything. You will introduce a forward diffusion that is ergodic. So for T large enough, you get pure noise. You have the time-reversed diffusion process with its own score, okay, which is a conditional distribution of Pt of X given Y. It works for a very large T, so that is to say you start from the pure noise case, you solve only the time-reverse diffusion process, and you will get an element, a sample of the distribution P0 of X given Y. So this is, as I said before, but if you follow this path, that means that you have to start again the learning phase and to learn this new score. That would be a nightmare. So the idea is don't do that because you have buys. Bayes tells you that pt of xy, what you need here is pt of ix, pt of x. So when you take the score of pt of xy, of course, you have this guy plus this guy. This guy, this is the unconditional generator, the one that you have trained once for all, without y. And this one, it's just a likelihood. So it's much easier to learn. Sometimes you even have it explicitly. So depending on the problem. So that means you can really, very quickly, once you have learned a generator of the prior, you can really design very quickly a biased generator that will generate images that are compatible with the observation y. So this is what happens here. I just pick one. I mean, I had tuned a generator to generate human faces. I tell it, you should generate something that is compatible with what I can see here, and it has given me that. So of course, it's not the same. There is no way it could have guessed that this guy was looking at the left, but you can see it generates a human face that is perfectly compatible with the data that is here. And this is done very, very quickly once you have trained a non-conditional generator. So that's funny for image, but you can do that now for imaging. It's the same idea. You will first train generators of what you want to image, for instance, a human body. So here you will train a generator, that is to say you will learn the score based on, let's say, a set of 1,000 CT scans of lungs. So you have 1,000 CT scans like that. You will learn the score of this guy. Now you have a perfect generator of realistic CT scans, high resolution. And now you can now go on the field, do some fast measurements, so sparse CT scans, very, very sparse. And now you ask your generator to generate high-resolution images compatible with the data that you have measured. And it will generate something very, very good images. Of course, it generates very good images because the generator only generates high-resolution images. So they always look good. They always look realistic. But sometimes they are completely wrong. So that's the problem with it. So it works well. So right from 2022, we could have very impressive results. But now we do know that we have to pay attention because, of course, the images, as I said, they always look good, but they can be completely wrong. Because if you trained your generator with people that do not have any tumors, there is not a single tumor in all the training sets, it will only generate images in which you have zero tumor. On the opposite, if you have trained only your generators with people with cancers, it will generate cancers at any sample. So you have to be careful when you do that. But it's promising. It's really promising because the quality of the image is very good, and it's the best estimate. It's really the best estimate given a prior that is highly informative. You tell it, my prior is the interior of a human body. It's not anything. So it works like that. So I think it's promising. So a lot of people are working on it, and I think it's quite nice. Okay, now I still have 15 minutes. This is it? Okay. A few words about the last topic I want to describe. Can we learn the loss function to make it more appropriate, to make it nicer, to optimize? So one idea is the one proposed by Enquist, and then a lot of people worked on it, in particular in seismology. Ludovic Métivier in Grenoble is working hard on that. And the idea is really to replace the quadratic misfit by something else. a kind of distance. It's not a distance, in fact. Let's say it's a similarity that comes from optimal transport. It's really how to transport. It's not a point-to-point comparison of for any time you compare this to this. It's really try to compare the two distributions. So if you have two time traces that are equal to each other up to a small shift, then the L2 distance will give you they are very far from each other. While the Wasserstein distance will tell you, oh yeah, they are very close. I just need to do that. So that's the way a Wasserstein distance works. And it has been successful on some examples because indeed it can reduce cycle skipping. Exactly the phenomenon I'm talking about. If we have a slight shift between two time traces, two oscillatory time traces, the quadratic distance is very bad, while the Wasserstein distance is much better to tell what is close to each other. So that's a possibility. People are working hard on it. Another one is a very intensive one, is to look after a nonlinear transform of the data, the synthetic data or the measured data, which is such that the quadratic misfit of the transformed data has better properties. So of course, people try to do that. So the C theta will be again a big neural network. So far, it has not been successful because, of course, you need to write another type of penalization here because you can imagine that if you don't make penalization here, well, there is an easy way. You take a C theta that answers always 0, and it's perfect. You have solved the minimization problem. So you need really to constrain the convolutional neural network so that it keeps a kind of expressivity property. It cannot be reduced to something that is not informative. And then you can try to learn both the C and the theta at the same time. And hopefully you will get something good. So people started to work on it 2 years ago. So far, nothing particularly interesting, but you never know with this big, deep neural network business. Sometimes you have a discovery. So, okay, we have to pay attention just in case it may work. And eventually, I will propose something else. It is, in fact, in the spirit, it's close to that, but I will help to build the C theta. I will not do it completely blind using a big neural network. I will help to build this nonlinear transform, which will help me to give me something, a new objective function that is better conditioned and that has better convexity property. How to build a nonlinear transform here R, which is such that this new objective function has better convexity properties than the original one, in which you just compute the quadratic misfit between the synthetic data and the true data. So just because if I write it directly, you will not understand, we will go progressively towards this new objective function. Here is an objective function that has very nice convexity property. It's this one, C minus C mes squared, because as a function of C, it's quadratic, so it's strongly convex, everything is perfect. So from the convexity property, this one is perfect. But of course, it's completely useless because I don't know C mes. So as a function of C, it's perfect, it's convex, but I cannot use it because I don't know C mes. I don't measure C mes. Okay, another attempt. I look at what I call the wave operator. In fact, this is a piece of the scalar wave equation that contains the velocity model. Okay, I will try, in fact, to work on the reconstruction of this operator. So, of course, I want to do something algorithmically, so I will need to discretize this guy. So to discretize it, I will choose a set of functions. So you choose your favorite functions. I don't know, small Gaussian peaks or stuff like that. And you project left and right this operator on this basis function. So you apply this operator to one function, and then you multiply by another function, you integrate in X over the whole domain, and that gives you, therefore, a big matrix of size, the number of elements of your family of functions. And I write this new imaging function. So this new imaging function is again a quadratic function. In fact, from the convexity point of view, it's still okay. Because it's very local, it's almost, I mean, it's not exactly quadratic, but it's still strongly convex in C. I mean, you can really keep track of where is C, and the place of C in this guy is explicit and simple, so it's still a strongly convex function in C. But, same thing as before, that guy, I don't know it. Because I know these guys, but I don't know the wave operator of the real situation. So it doesn't work. Now, instead of picking myself a set of basis functions, I will construct them in a very special way. I will look at the snapshots generated during the experiment. What are the snapshots? These are the spatial profiles of the waves during the experiments. So I have a certain number of sources. So each source generates waves. I look at them. I discretize in time. So for each time, poof, I take a photo, and that gives me a spatial profile, and I collect that in a big family of snapshots, of basis functions. So of course, these functions have no reason to be orthogonal with each other. So you have to first orthogonalize them. So use your favorite orthogonalization algorithm, Gram-Schmidt. You must have seen Gram-Schmidt when you were young. So you orthogonalize this set of functions, and you have now a basis of functions. And you do the same thing. You build the projection. I mean, you apply to the wave operator, left and right, these basis functions. And you write this objective function, the misfit between the synthetic one and the measured one. And then you will tell me, OK, it must have still nice convexity properties, but I don't know that guy, and I don't know it for two reasons. I don't know the true wave operator, and I don't know the snapshots. I can't see what is inside the medium. Yes, but if you are a mathematician, you don't give up. And in fact, that guy, you can compute it without any error from the data. So you don't know the wave operator, you don't know the snapshots, but from the data, and only from the data, you can compute exactly the projection of the wave operator onto the orthogonalized snapshots. I will show you the algorithm here that tells me that indeed, from the data, by a series of algebraic manipulation, a Cholesky factorization somewhere, you get exactly the expression, the exact expression of that matrix. So that tells you that this guy is a perfectly legitimate objective function. This guy, I can compute it from the data. This guy, I can compute it if I have a candidate velocity map C. And the overall objective function has nice convexity properties. So that's, in some sense, in line of learning the loss function. We have changed the misfit function in a data-driven way and with a little bit of math. And now we do have some hope to be able to solve the full waveform inversion problem, because indeed we can show that if the space of snapshots is rich enough, that is to say if you have enough sources illuminating the medium from different angles, then the snapshots are very, very diverse. And then you can show that indeed this guy as a function of C is convex. And if it is convex, it's much better. For instance, remember that example. The first academic example I have shown you, that's a very simple medium, two homogeneous half spaces separated by an interface. That's the landscape of the fuel waveform inversion quadratic data misfit. So with a lot of local minima everywhere. Now if you apply this method, poof, you have a unique global minimum. The function is convex, so now you can run whatever optimization algorithm you like, gradient descent, you start very far, it will go directly to the global minimum. So that's something new. It's in the line again of learning the loss function. We have changed the loss function compared to standard fuel waveform inversion, but we get now a formulation with better properties. So you can apply it then to different test cases. So Jean Virieux told me you should try the camembert problem. So why camembert? He told me that. It's because when you try to reconstruct a fast inclusion in a homogeneous medium, the typical FWI image looks like something like this. It looks like a cheese that is melting. But okay, this is because this is a local minimum. Here, the starting point of the gradient, it's a Gauss-Newton, I think. Here, it's a Gauss-Newton algorithm. The starting point is just a homogeneous medium, blue. You start from everything is blue. You run a Gauss-Newton algorithm, and you end up, this is a local minimum. You're trapped. While the ROM, I mean the minimization of this guy, okay, it goes to the fuel picture without problem. And the same thing, in fact, is not more difficult than the previous one, but maybe it's more interesting from the application point of view. It's the imaging of a salt, so it's a seismic exploration. Here you have a salt body, which is a fast inclusion. And as usual, it's very difficult to see, to image a fast inclusion. So FWI is again trapped in a local minimum, while okay, ROM can do it. Okay, 4 minutes, that's perfect. I still have 2 slides. This is not the end of the story. So far, for this method I've just shown you, we have one limitation. That's part of the mathematics that we need to apply to compute the AROM from the data, is that we need some reciprocity, and that means we need collocated sources and receivers. So that is to say, we need transducers. Otherwise, we are in trouble. So we are working on it. I don't say this is impossible. I just say we have not yet done it. So we need collocated sources and receivers. And of course, the first idea to go beyond this limitation was to use passive imaging, because I think you are more or less familiar with passive imaging. The fact that by collecting the signals recorded by passive receivers and transmitted by, let's say, ambient noise sources, by cross-correlating these signals, you can reconstruct the Green's function between the receivers. You can apply that here, and then naturally, you will have collocated virtual sources and receivers because you have transformed your receivers into sources. So we did it, and in fact, indeed, it works. The method is perfectly appropriate for this method. And very recently, we went to any type of waves. What I have shown you was just for scalar waves, but in fact, the same principle can be used with vector waves. But again, we need a kind of reciprocity. That is to say, if you use vector waves, you need to be able to transmit, in some sense, all polarizations and to record all polarizations. You need the same polarizations as input and as outputs. That's important. Okay, so that was my conclusion. So you have seen the last method is very surprising because we have a situation in which we don't know the wave operator, we don't know the snapshots, but we will build something from the data that is related to the wave operator and to the snapshots. And this something will be used to build a loss function which by minimization will give you a relatively easy estimate of the medium you are looking after. So that's the main point that we are working on today. As I said, we started to work, of course, with active imaging configuration, but passive is okay. Vector waves is okay. We still have to solve this issue of collocated sources and receivers, how to do that more efficiently. We are not yet there, but almost. And I will stop here. Thank you.